Hi everyone. Okay, we're finally going to tie everything back to circles, what we've been working on. So we've talked about linear velocity, which is just like the speed of an object as we usually think about it. And we've talked about angular velocity. And now we want to talk about linear velocity when you're moving around the outside of a circle. So circular motion. And we have this idea that velocity is distance traveled over time, and we're using this little s that's very traditional in calculus to represent distance traveled. And conveniently, that matches up perfectly with the slight shift in the thinking that we want to do for circular motion, where the linear distance is actually an arc length. So you'll see that I switched from little s to big S, but here they're really interchangeable. It's distance traveled, which in the context of moving around a circle is arc length. So we start with this v equals arc length divided by time, and we can actually play with this a little bit. So this is really the basis that you can always go back to. But just to see what happens when you're talking about a circle, we know that as long as we're working in radians, that arc length is r times theta. So we get actually that velocity is the radius times the angle divided by the time. And we can even play a little more. We can separate that r out of the fraction and get r times theta over t. And if you remember from what we were just looking at, theta over t is angular velocity, which we've called omega. So this is really r times omega. So you can think of linear velocity on a circle as the radius times the angular velocity. Sometimes that'll be really helpful, sometimes it's not what you need, but it is something you can think about. Again, number one thing to remember is this, but you can get to this radius times angular velocity as well. So looking at an example, we have a particle traveling around the outside of a circle with diameter 6 inches. Okay, so be careful about that, which means the radius is actually 3 inches, which seems to be my favorite circle for all of these problems. The wheel, this is not a wheel. The particle, don't know what I was doing in there, is rotating 2 radians per second. We want to find its linear velocity. Okay, so using what we just found, we can say the linear velocity is the radius of the circle multiplied by the angular velocity, which is 2 radians per 1 second. So this is going to be 6 inches per second. And that is really slick. That's really nice here. Just to show you, we can get there just using dimensional analysis or a little bit different thinking. We could also say, okay, we know that we're going 2 radians per second. And again, you don't ever have to write radians, but sometimes it helps my thinking. And here we can use dimensional analysis if you're really connecting with what a radian is. A radian is the angle that you have to rotate through in order to travel your radius distance around the outside of the circle. So in this case, the radius is 3 inches. We rotate through 1 radian to travel 3 inches, and this will work out exactly the same, 6 inches per second. I'm sure there's other ways you can get to approach that as well, but that's the idea. So linear velocity, I'm not changing the definition, I'm just pointing out that we get an arc length formula in the mix when we're doing this, and that can be really helpful. Okay, thanks for watching.